Hello boys and girls. In this video we're going to go a little back 2 weeks ago to some of the things I said in the set theory video where I introduced this book. On the one hand, and on the other hand we're going to touch vaguely some of the data structure concerns that popped up in the Libra white paper, the blockchain white paper that I reviewed a week ago. In particular, we are going to talk about, and now excuse my pronunciation, hereditary finite sets. Hereditary finite sets. So a particular kind of finite sets, and in particular, this makes for a model of Zermelo-Fraenkel set theory if you remove the axiom of infinity. In that sense, it ties back to the broader scope where I'm getting with the channel. And what we are going to do is we are going to programmatically show how to generate all of these sets. In a sense, we are going to show how we can generate all sets without elements, meaning everything is just based out of the empty set and sets composed from the empty sets with simple operations. And by set, I mean here set in the standard set theory context where they have always a finite depth, are well founded, as you say. And so we're going to come back to this picture. This represents a particular set, and we're going to do some Python, and exactly this picture will pop up again, and then you will understand it. The construction that we are going to do is by starting with the empty set and applying several power set operations. And since we are going to use a programming language, so we have to do some implementation, this will be in a sense more concrete than just doing first order logic, for example, to characterize sets. And this is also how it relates to this paper. This is the paper that was referenced in the Libra white paper. They mention Avl here and reference the paper, and they actually do this like a couple of times. The Avl tree is basically one possible implementation for sets, like for collection of things that have a certain order, and this particular implementation enables you to search for things in the set very quickly and insert and remove from the set, and in that sense is very important and thus like fundamental and basic computer sciencey data structure that you will encounter if you learn that. We're going to strip down the implementation because we're not actually interested in any sort of efficiency. I will just flat down this notion of set to a list, and you will see how that plays out, and then show how you essentially take the power set and get to this collection of sets that make for the model of the set theory. I want to note that this idea that we are going to perform, where you take a set and then take the power set and iterate this process, this can of course be extended beyond finite sets. So the von Neumann universe takes that and this sort of iteration idea for every ordinal, even if the ordinal is infinite and uncountable and so on. And then in that sense, there's also like a general version of this sort of class of sets, and also classes that are in between. They're not just the finite ones and not the general ones. And so all these concepts are studied in mathematics, but we are in this video concerned with concrete stuff. One last word on the Avl trees. So this is this computer science structure that I talked about. Here is this mesmerizing GIF of, in this case, letters that are ordered. So you see that they are the letters are coming in and then assembled in this binary tree, and assembled in a way that is in accordance with the order of the alphabet. So in the end, A will be at the very left side, and so on and so forth. And what they do here is this left and right rotation, where this tree is going to be balanced, and so on and so forth. And in the end, you have this balanced sequence, A, B, C, D, E, F, K, H, and on the left side are the lower letters in the alphabet, on the right side are the bigger ones. And we, as I said, we're just going to flat this down. For us, a set, for us in this video, a set is something very like a brutal implementation of the idea of a set. It's just going to be a list which is sorted and has no duplicate entries. So if you have a list of numbers, then 1, 2, 3, this collection, this list would be considered a set, but not 4, 3, 1, because it's not ordered in the order that the standard order, as well as 1, 4, 4 is also, in this case, this list is not a set because it has 2 4s in it. So a set is going to be just a list, which is a kind of brutal implementation, and where we have the conditions that no entries are duplicated, as is the case for a set. And we are also considering it to be a set as soon as it is ordered. And this, of course, diverges from let's say, the standard set theory, because a property of the set is that as such as the set itself, it does not have an order associated with it. This is then the case that for all finite sets, you can actually order them. So we don't commit too much of a crime here. And also in the full stronger set theory, like the standard set theories, once you add the axiom of choice, then this actually implies also the well-ordering theorem, and so then all sets in principle can be well-ordered. Whether you like ethically agree with that or not, that's another question. But as long as we are in the finite realm, I guess, as long as we're just considering finite sets, then those can all be well ordered, and in that sense, it's fair enough to consider them as a list. Okay, here's another example. Here you see CD, and not all letters in the alphabet are represented in this set, like in this tree that captures the elements in the set. And wherever there's something missing, let's say between the W is missing here, for example. So then the endpoints V and X, they represent sort of an interval with a lot of missing things. And so this object, this tree, represents a subset of the whole alphabet and put in order. Okay, I think just from the pictures, you might get the idea. Of course, these objects, the Avl tree, they has some nice mathematical properties in terms of efficiency, and that's also why the reason why they talk about making use of these data structures to optimize the conventional blockchain as you find it on Bitcoin, and so on and so forth. If you remember, or if you have seen this video, I talk about this Libra chain and this kind of tree structure docks to it, and this is going in that direction. Maybe I come back to the topic, but nonetheless, now you have an idea of what I talk about when I speak of finite set. I speak of a particular implementation, a crude one. And so lastly, before we get into coding, this is the video where I rant about sets, and this is the video where I talk about the Libra white paper. So you might want to check that out and subscribe to my channel and like, and so on and so forth. Okay, so as we did in the last time, I have here my editor. I do some Python coding, and here I can run the script. For example, I can run this script and it prints out this message. And this video is actually hopefully going to be not as long, because we actually have to implement one sort of function. We're going to implement a power set. And then we are going to use that iteratively, as you have seen in this short Wikipedia clip. You will see in a second how this works. And that's really it. And then we're going to compare it with this graphic, and you will see that things match out. So okay, by a set, as I said, I consider, for example, that this would be a set. Right? This would be the set holding the letters A and B, or this would be another set that holds 3 elements, 1, 2, and word. And a set can also hold another set, so this would also be a set, where one element of this set is another set. And in particular, what is also a set is the empty set. Morally speaking, you could argue about the validity of such an empty set, but it's certainly a practical one and makes a lot of operations smooth, just like the number 0 makes some natural number computations easier. So we are not going to debate that in this video. Also, I like to debate these kind of things. The power set is easily defined. The power set is the set which holds all subsets of a set. Okay, we are going to leave the this for later. I'm going to call this some basic set, some simple set. Let's say some small set, for example. And now we're going to define this power set operation. And again, I want to emphasize that this is a crude kind of set, because it's actually, a list is not a set because a list is ordered, and a set is generally not ordered by definition. Although you can put the elements into an ordered list, and basically this ordered list represents our set. And also, this is not encoded by the code that we are going to code in any way, but this would not be considered a valid set simply because elements are repeated. So we have to watch out to not make this mistake. And I'm going to define the power set operation. Yeah, I could say power set. This is the function. And this is going to take some set. We're going to call this set X. Yeah, this is a generic set. And this is going to return the power set PS return. And here is going to be our algorithm to compute the power set. So for example, if this is a set, then the power set is the set of all subsets. So it would look like something like this. So the power set would hold, the empty set is a subset, then it would hold each of these elements. Come on. So these are all the one element subsets. And then it would hold word as a subset, but then also it would hold this set. This is a subset of this set, and so forth, on and so forth, and then it would also hold, for example, this set. Right. So the power set is a set of our subsets, and it can grow quite large. In particular, actually, it grows exponentially with the size, with the cardinality of the input set. And what we're going to do here for the implementation is we're going to code it up in a very standard procedural fashion. We're going to define PS as basically a set to start with. So what we know is that the power set always has the empty set in it. So this is a set which holds the power set, and now in some loops we're going to add all the elements that are necessary to make for the set. So let's also print stuff out here. We say line break, and then computing the power set of X, and also start with, we're going to do a lot of comments in the computation so that we can see what's going on in the end. Start with this PS here. That's going to be PS. Right, so if I go with power set, compute the power set of the set which holds the letters A and B. Then this is then the information that we already get. Computing the power set of AB, start with this set. And now it's actually pretty simple to define how to do that. So for each element in the input set, right, we're going to go through these input sets. We're going to add a bunch of subsets to this starting power set. We say, well, for all subsets that are already in this, we're going to compute an extended subset, which is the subset plus this element, and then enrich PS by just adding this extended subset. So here you might want to understand some of the Python syntax. So in Python with lists, you can add them just like numbers, and then they are just concatenated. So here I just concatenate another element. Right? I extend the list with this element, and this element is just the subsets that are already in it plus this new element. And this is already the bulk of what we're going to code here. This is already the implementation. We can make some more information here. Consider an element, this element. You know, this is all printed for every point that we are in the loop. This element and subset. Well, this subset. Add, and then we're going to add this extended subset. Yeah, and then we can also print out where we are currently with this PS, as we did above. Okay, and if we now run this here, we can watch what happens. So here we start. We're computing the power set of AB. We start with this power set, which just holds for now the empty set. We're considering the element A and the subset, which is already in it, the empty set. So this extended subset is the empty set together with this element A in brackets. So this is what's going to be added as an element to the power set. Okay, so from here we go there. And then for the first outer loop, here inner loop, PS. Previously there was only the empty set in it, so he's done with A. And now he considers the element B in X. And now there are already two subsets in PS already. So firstly the empty set, so we add this one. And finally, A, which in the previous iteration we just added there, right? So he adds the element B together with A. So this element is constructed and added, right? And this is then the final power set, right? This is the set of all subsets of this one. We can also do another example. Let's go with X, Y, and Z. So what happens here? Well, I mean, it might be easiest to just look at how successively all these elements are added, right? So first X is considered as an element, and then Y, and all the combinations are constructed with this extended subset construction. This is added, and then finally Z is considered. Z is added as plain Z. Z is added together with X. Z is added together with Y, Z is added together with this long set, and eventually we get the set. The full set also as subsets. Okay, so this way, as you can see, right, we can play this game also with, I don't know, with list range 8 to 11. So here we look at the list 8, 9, 10, and this is of course the same thing with the x, y, z. This will blow up quickly, so I will not go to very big examples, but if you add another element, well, you see for the computation of the power set of this 4 element set, this already has actually 2 to the power of 4, so this already has 16 elements here. And that's our kind of nasty implementation of the list as the set as a list. I want to add here that Python, of course, already has an implementation of a set data type, and surely the implementation uses some more clever underlying structure. But eventually on the hardware, where all the data elements are put into some place in some sort of register, and the orderless set is really a mathematical notion, right? Whenever you deal with quote-unquote real things, then you already have them in order, you can put them in order. And the idea that you might have a notion of collection which inherently has no order, such objects which you describe if you do Zermelo-Fraenkel set theory and reject or negate the axiom of choice, then it's the case that there are such objects which you cannot well order. They are a little bit away from all these implementations in which you just deal with objects at very least with zeros and ones on your computer that are already in some order. So the ordered notion of sets that I discuss here, it's kind of inherent to the finite world and finite sets in particular. Okay, going to remove these print statements here, and now finally, it's very simple actually. The hereditary finite sets are all the sets that you get using the repeated application of the power set, and starting not with an UR element, not with an element that's different than a set. For example, in a sense, this A and B or this word is not a set in itself. In some semantics anyway, in the Python semantics, let's say. But instead, what we're going to do is just start with the empty set and power up from there. And we're actually going to do 5 iterations of that. So I say for k will be our iteration level in range 0 to 5, so range 5. We're going to print so we're going to construct a set of all this hereditary finite sets, and we're going to we call this V K. And where does this the V letter come from? Well, I'm just using this notation, right? V, and I use a small v for respecting Python notation standards. And so Vk is going to be our this set. So we're do they explicitly say it? Yeah. The base case is that the empty set is one of the sets, and the recursion rule is that you put all sets into it that you already have, and this can also be achieved, as they explain here, by using the power set operation. And you know, we start with V0 is the empty set, and then we get V1 by applying the power set operation, an implementation of which you just give once, and then given the V1 we apply the power set of this again, and so on and so forth. And if we would do this infinitely many times, then we just would cover all these finite sets. We're just going to go to level 5. So I loop through this. I say if k is 0, well, then V is going to be the empty set. This is our base case. And I'm going to print to answer the question what it contains. I will just say nothing. And otherwise, go on. We're going to define this V of the stage as the power set of the v we already got. Like this is the v we get from the previous iteration. And then I will also print all elements out here. So I say for element in enumerate v. So I'm going to iterate through all the elements that I get out of it, and I add an index so I know in which row I am. Print, and we're going to print the index, and we're going to print the element. Okay, so this is the code. We are not going to code any more than what we have here. Let's actually start not with 5 but with just 0 and see what happens, okay? Moreover, I might actually comment out this for now, so there's not too much information being printed. So I will just print this here. Printed nothing. Okay, I think I have at least to go to 1 here. So for 1, like the k is 0, he sets v to the empty set, and then he prints v0 contains nothing. Okay, that's clear. Then let's go 2 levels actually. So the first level is here, actually still contains nothing, of course. And then on this universe level v1, right, there's actually only one set that is contained in it, namely the empty set. Like this is just the power set of the empty set is just the set holding the empty set. Okay, this might look a little bit abstract, but let's go 1 level up. So again the base case nothing. In the v1 there's just the empty set, and come on, what am I doing here? Did I not go up to level 2? Sorry. Okay. I have to go up 1 level. And now after this comes the universe level v2, and this already has 2 finite sets in it. On the one hand it has the empty set, and on the other hand it has the set which just contains the empty set. So this is really the universe 1. This is the universe, like universe 0, universe 1, and this is the contained in this universe level. And then if you go even further up, then we see the universe level v3 already contains 4 sets. Contains these sets, and then it begins to contain elements that have more than 1 set. I think I can even go more. Okay, and then eventually on this universe level, and this is the first universe, the 0th universe, this is the first universe, and then these are the things that were already contained here. But beyond that, they start containing bigger and bigger sets. And what we find here, like if I would try to go up, I think I cannot actually compute the 6th one because it already explodes. Let's see. Yeah, so it tries to compute this now, but it stalls. Eventually, in this iteration of power sets, you get more and more of these sets on these universe levels. And oh yeah, now it was just coming down. So this already has 56,535 different sets. So this is one set containing a bunch of stuff. Actually, there's one more because index 0 is also there. So you see this like blows up exponentially. Like exponentially, and so on and so forth. So if I would go to the level 7, I probably would not stop today. And you see, I generate these sets, and these are really all the sets I would get from also this definition, right? We start with the finite set that is the empty set, and then consider all sets which are made by taking sets from this collection already and putting it into them. And in this case, like in this way, we generate all like sets, where sets is something that does not actually hold any like ur elements like A, B letters and so on, but are just made up from the empty sets. And if we would do this like iteratively an infinite number of times, then eventually we would go to like all these, all these VKs, they are all huge but finite sets. And if we like iterate this to the first infinite cardinal, like infinite many of times, like to the first infinite ordinal that corresponds to a cardinality of infinite many sets, then we would get V omega holding all these sorts of sets, holding all these finite sets, and that would actually already make for a model of the Zermelo-Fraenkel set theory, meaning all the axioms are respected, all the like in this collection of these finite sets, all the axioms hold true except for the axiom of infinity that says there is a finite set, an infinite set, because in all these iterations that we do, we never like inside of V omega we never find an infinitely big set. All these sets are a finite size. There are like if you do this iteration infinitely many times, then you get infinite many sets, but none of these sets is an infinite one. If you know what I mean. And the V omega is also actually also countable, so it's not a continuum or anything in between. What's also worth noting is that there is like this age-old from the 30s bijection between V omega, right? V omega contains a lot of different like strange-looking sets of various depths. Yeah, right. The VK can have a depth of K, like there are sets in sets and so on and so forth. But there is since this is still like the collection V omega is still infinite but countable, there is this bijection to the natural numbers, and it goes like this. You say you have this bijection F. F from 0 is going to be the empty set, right? You put the number 0 and the empty set into correspondence, and then whenever you have another number, then you do you represent it in binary format. Basically, you do a decomposition in powers of 2, right? And the value of this number is going to be the set holding other sets of this sort, where recursively the input value here is going to be the power of 2. So I give you an example. What would be a good example? If we take, what is the seventh such set, right? So 7 is 4 plus 2 plus 1. And so 4 is 2 to the power of 2 plus then also 2 to the power of 1, making for 6, plus 2 to the power of 0. And so we know that the power, like 0 is a power, so f of 0 is in it. 1 is a power, so f of 1 is in it. And 2 to the power of 2 means f of 2 is also in it. And what is f of 2? Well, some sets holding the power 1. Okay, maybe this was a little bit confusing. I can do it here in text. So, okay, f of 0 would be the empty set. Then f of 7, for example, would be f of 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0, right? So this would be a set containing f of 2, f of 1, f of 0. And then now you can compute what this is. Well, this is the empty set. This is 2 to the power of 0. So this is the set containing the empty set. And this is 2 to the power of 1, right? So this is the set holding the so the set holding f1. So it's set. So this is what you get, right? And if there was a higher power, like if you could consider f to the power of f of what would be good composition 13, then this would be okay. Good question. So you have I think this should be to the power of 4. The 3 should be in it. This would make for 8, mean 5 left. So no 2 to the power of 2, but 2 to the power of 1 plus the power of 0. So this would again be a set of 3 elements where the f to the power of 3 is also in it, which means you get the shift. It's recursively defined, and in this way you also get these kind of the sets. This would have, like, implementing this function would have been another way of like generating all the sets, but then I would have to make the decomposition into powers of then I would have to make the decomposition and consider all, like, find out what for the input numbers are the powers that are belonging to it. But what we can do is we can also print this index j of the element in binary, and then at least you get this correspondence. So here should show up, this is the 7, as you said, yeah? But 2 to the power of 2, 2 to the power of 1 plus 2 to the power of 0 makes for this set, and so on and so forth. 13, 1. Now this is a set with 3 elements as we conjectured, and this is then f of 5 and so on and so forth. F of 8, f of 5, whatnot. You get you catch my drift, I guess. I think that's it for this video. I could say more, of course, about Avl trees, and I might, but I really try to keep this video short, and that's why I'm focused on one topic. I hope that was interesting. I think this is actually a very good access point to discuss set theories, right? Because if you discuss this class of sets, then there are this very simple, like as you saw, iterative way. The power set is easily coded up, at least for the sets. These sets made of lists, and then you already got so many sets, so many finite sets that are actually closed. Basically, these are all the finite sets you can wish for, and you can already start checking all the axioms. Check if these are actually theorems of the model you have thus constructed. So I think this is actually a good access point to sets. It must be noted, however, of course, that set theory was invented not to talk about finite sets. The set theory is actually the main point of set theory is to talk about the strange thing of, like, infinitely growing cardinals. Historically, that's one main point anyway. And so the harder to grasp aspects of set theory come into play when you go beyond v omega, right? I talked about v omega plus omega being a good playground to do normal math, to do physics as well. All the functional analysis should more or less fit into that, and that's what you get if you take v omega, like this set of infinite sets, and then start to apply the power set onto this infinitely many times. And each time you do this, you actually get a bigger infinity, and things are starting to get weird, and you are not able to prove the orderability of these sets anymore. So they behave very different. There are many theorems of the model of set theory I have constructed in this video that don't hold for sets in general. For example, for finite sets, it's clear that if two sets have different size, like if this is set A and this is set B, and set B is bigger than set A, then the power set of this smaller set will be smaller than the power set of this bigger set. So this size relation holds if you go up this power set level. But as soon as you go over the V omega, over the first infinite set, over a first infinite set, then this actually doesn't hold anymore, because infinite sets are weird in the way that it's not like you cannot judge the cardinality just you cannot guess it usually trivially, but by just looking at the sets themselves, like just spotting them once. But nevertheless, okay, the collection of finite sets, all the Zermelo-Fraenkel set theory axioms hold, except for the infinite set axiom, and that's of course the postulation of a simpler infinite set that is a good model for the natural numbers. This infinite set V omega that we constructed is actually it's an infinite set, so I don't want to say it holds more elements, but it holds a broader variety of elements. It's still countably infinitely many, but this is a nice playground collection of finite sets that is richer in structure than the natural numbers. Okay, thanks for watching. If you are interested in these topics or some of the angles that I touched, then tell me which ones and I might get into them in more detail. Otherwise, I might make another video on these class of set and look at the different set theory axioms and see how they hold for them. Take care.